Up to now we've talked a lot about Laplace transforms and the S-domain. However, there's different ways of representing dynamical systems using what's known as state space representation. So as we've seen, dynamical systems are things which change over time, and they can be captured using differential equations. So we can model what's going on in terms of basically the state of the system, and it could be in terms of things like, let's think about a car. The state of a system would be like the state of a car could be, where is it in space? What's its velocity? How are these things going to relate? The driving force from the engine, and so on. And we can capture all that with a mathematical model, which will result in typically a differential equation. Again, we could model the dynamics of a motor. In fact, we've already done that. So we apply a voltage to a motor. Slowly it will start speeding up and speeding up. Again, it's a dynamical system. We can model it in terms of things like the current flowing through the armature and the rotation of the armature itself. Another example, which is in this case purely electrical, would be applying a voltage to an RCL network. And how does the voltage across the capacitor change as a function of time? How does the current in the circuit change as a function of time? All of these things are dynamical systems. A nice simple mechanical system is going to be the mass spring damper. So we're going to have a mass which is connected to something you can't move through a spring and also through a damper. We give it a pull. How does it move as a function of time due to the force applied? One important aspect of thinking about dynamical systems is thinking about the state. So what state is the system in? The state is something which basically can predict future behaviour given the current circumstances. And typically it's determined by energy storage. So it could be a pendulum moving backwards and forwards, and you can think about the kinetic energy and also the potential energy in the system, which we can then capture maybe in terms of the angle of the pendulum. And we can plot these things out. We can plot how these things change as a function of time. And if we want to, we can plot one state against another. So that would give you a typical phase portrait. However, we're not looking into the fundamental aspects of dynamical systems from a scientific perspective, and that's what lots of scientists will be doing. We're more interested in from understanding it in terms of engineering. How can we model a system so we can actually understand it and also be able to control it? So depending on the kind of system, you might think of different kinds of energy that they can store. A capacitor, for example, can store electrical energy, and it's basically a function of capacitance, but the variable, if you like, is going to be the voltage. An inductor will store energy in the magnetic field, which is affected obviously by the inductance. But again, the important parameter is going to be, the important variable is going to be the current flowing through it. Then we have mechanical systems. If it's a linear system, we care about the mass, we care about the velocity it's moving at in order to calculate the energy in the system. Rotational systems are similar, except we care more about rotational velocity than linear velocity. And we have, pressure, and we have temperature in pneumatic and thermic systems, and so on. The important thing about state space representation is it's a way of describing, if you like, a dynamical system, which could be fundamentally a high order thing, which could be written down as a high order differential equation. State space representation is concerned with writing it down in a way that represents it in terms of lots of first order ordinary differential equations. And because of that, we can write it in matrix form. And the typical matrix form is going to be the differential of the state equals a matrix A multiplied by the state vector plus a matrix B multiplied by the input vector. So x dot then is going to be the state derivative, which is a vector. A is going to be a system matrix. X is going to be a state vector. B is going to be the control input matrix. And U is going to be the control input. We can similarly describe the output of the system, which is going to be some function of the state of the system. And typically this is going to be written by the matrix equation y equals Cx plus du, where y is the output of the system, C is the output or observation matrix, X again is the state vector, and D is the transition matrix. So D basically tells you how the input directly affects the output. And U again is the control input again. So, just to point that out one more time, two very important equations, you need to know these off by heart. X dot, where X is a vector of states, X dot equals AX plus BU, where A is the system matrix, X is the state vector, B is the control input matrix, and U is the control input vector. And the output is given by the relation y equals Cx plus du, again all matrix equations. Y is the output, C is the output or observation matrix, X again of course is the state vector, D is the transition matrix, which basically relates the output directly to the input, to the control. Now, we've used signal flow graphs before, and it's a nice way of, if you like, writing things down in a circuit diagram form. So you show how the information flows between the various sections, and you can implement transformations, and you can implement addition and subtraction and all this kind of thing. So let's think about our state space equations. X dot equals AX plus BU, Y equals CX plus DU. We can write a signal flow diagram. In fact, we can solve the equation using them as well, right? So let's write it down and try to understand what it means. So first of all, let's look at this drawing and see what the terms are. Well, first of all, UT, right? That's the input. That's the input control. YT is the output of the system. And what we're doing here is we're actually saying, well, if we give this system an input UT, this is the signal flow graph, which will actually generate the output Y of T. So all the matrices are basically put onto this system. We've got the A, the B, the C, and the D matrices. And we've also got, at this point here, after this integrator, we've got the state X of T. So let's think about how this system works. Let's first of all do the output equation. Y equals Cx plus du. So here's the input. Input, first of all, goes up here, multiplies by D. So here we have du, and that's going to be added on to something to get the output. So that's the first part of the output. And here, right, coming out of the C here, we have the X state here going into the C, so we get Cx coming out here. So Cx here plus du here gives us the output. So that's the first path done. Secondly, let's consider now the X dot and the X. So what we're saying here, X dot, that is the differential of the state, and X is the state itself. And if we want to get from the differential to the state, we have to integrate it. So what we have here is we have a representation here of the state differential, which we then integrate to get the state. So that's fine, we can do that. So let's now think about how we build up X dot, right? How do we build up the differential of the state? Well, that's this equation here, right? So we have to say X dot, which is here, right? X dot is going to be A times X, so this is X here, multiplied by A, plus U times B here. So this is the BU, this is the AX. We add those together and we get X dot. Like I said before, the X dot is then integrated to get X, and X is then used to generate part of the output as well. So this signal flow graph is actually solving the equation for you, right? This is actually, if you like, if we could implement this, let's say in Simulink, it would actually calculate all the outputs from the system. In fact, if we had a numerical integrator doing this, in fact, you can do that. You can solve a state space equation using this signal flow graph way of actually writing things And you could just directly do that in Simulink. So it's one way of actually solving the problems. It also gives you a bit of insight into what's going on. So, like I said, we can do that in Simulink. And it's pretty much just a question of dragging the blocks in that we just had on the signal flow graph. The only thing you have to watch out for is make sure that the multiplications are appropriate ones. So you want to make sure that they're actually doing the appropriate multiplications, the AX and the BU, CX plus DU. Make sure that they've got the right dimensionality. But basically, that's what we're doing. Here we've got the U coming in. And in fact, we're scaling it here as well. So this is going to be the U. U times B comes out here. Then we're adding that with X times A coming in here. And that at this point here, we've got the X dot. 1 over S, that's an integrator. That gives us the X. And then we scale the X with C and add on U times D. Add them up and generate the output. It's that easy. So in a simple example of a state space representation, we might have, let's say we have a situation where we've got a single input and a single output. Okay, so state space models can capture much more than that. We can have multiple inputs and multiple outputs. Well, let's just take the simplest case now, that we've got a 1-by-1 input, right? So it's a 1-by-1, it's a single value, and we've got a 1-by-1 output. Even in this condition, when we've got a 1-by-1 input and 1-by-1 output, we still quite often would have a multiple dimensionality state vector. So let's look at the state vector. So X is going to be n by 1. It's going to have n values in it. That means the A matrix has got to be n by n. It also means the B matrix has got to be n by 1. And the output X dot from the first equation has got to be n by 1. So we've got n state differentials in here. We've got n by n elements in the A. And we've got n by 1 in the state, n by 1 in the B matrix, and a 1 by 1 in the control input. The output equation is going to be 1 by 1. So if we've got an n by 1 state, that means C has got to be 1 by n, right? So we have to always multiply matrices so the inner dimensions match and the outer dimensions give us the dimensionality we want. Right. So we can think of that quite simply then. Also from the first example, the output of this has got to be n by 1. So this has got to be n by n, and this has got to be n by 1, because you've got the n by n of the same dimensions, and then the overall output is going to be n by 1. Same for here. N by 1 times 1 times 1 means that the output of this multiplied by that is going to be n by 1. So, like I said, the idea of state space representation is to write high-order differential equations or high-order systems in a set of first-order differential equations, and then if we do that, you can use this representation, because that's what this is saying. It's saying the differential of the state equals something to do some some multiplication of the state plus some input value. It's basically it's in the rows you've got first-order differential equations. And then we've got the corresponding output equations. But you can always rewrite a second order, say, or a higher order, in terms of first order differential equations. Let's think first of all in terms of a second order differential equation. Let's say the second differential of x dot dot, is some kind of function of x and x dot. We can define a y, right? Let's say y is the first differential of x. If we differentiate y, that gives us x double dot, right? So y dot is now x double dot, and double dot is the thing we started with, but we want to get away from those. But x double dot is this function f of x dot, so y dot is also this function function of x and x dot. So we can end up writing two equations now. We've artificially generated this one, right? So we've x dot equals y, we can say that, and y dot equals the function of x and y. So we've ended up starting off with something which is second order, and we've ended up with two first order expressions. And that's the general idea. And we can carry on as many times as we like in order to do that. We can end up splitting up something, and that's a third order equation. So we have a x triple dot equals a function of x dot x double dot. We say y equals x dot, z equals y dot, which is x double dot. So now we can say z dot equals x triple dot. So z dot equals function of x dot x double dot. And following it through, we see that now what we have is we have this, that x dot equals, sorry, z dot equals a function of x, y, and z. In fact, we need to put, yeah, it is a function of those. Y dot equals z, and x dot equals y. So now we've split it up into 3 equations, and you can carry on to n equations with this approach. So let's just think of one particular equation now, and we'll just concentrate on this because this is going to be a relatively simple case to do, but it's nice to do something directly from a differential equation. What I tend to do also, by the way, is even when I'm analysing something from a real system, and you can always generally write it in a compact way like this, with no coefficients in front of the d squared y dt squared, with a coefficient in front of the first differential and another coefficient in front of the no differential term, and another coefficient in front of the control term. Even if these expressions a1 and a2 and b1 are actually quite complicated, I find it actually helps to break it down in this way. So let's now rewrite this so in a way that we can start actually analysing. And the way to start is, first of all, to make sure there is only a unity in front of the highest differential, and then we have the highest differential rewritten on the left and everything else on the right. Right, so now we've got our d squared y dt squared equals, we move these over to the other side, minus a1 dy dt minus a2y plus b1u. Right. Because this is a second order differential, what we can see is the state variables have got to be one differential less than that. In other words, they're going to be first order. So let's choose some state variables. Let's call, it's not going to be u, because u is going to be the input. So the y is going to be a state variable. Let's call that x1. And let's call dy dt, let's call that x2. If we differentiate x1, x1 dot, we get dy dt. So we immediately see that x1 dot equals x2. First state equation. Then if we differentiate x dot, sorry, I tell a lie, x2 dot, sorry, we differentiate x2, we get x2 dot, which equals to d squared y dt squared. So we can now substitute these into the equation. Right, so the first expression here goes to x2 dot, and then we substitute in dy dt, right, which is x2, that goes in here, and then we substitute in y as x1 here, right? So we end up with x2 dot equals minus a1 x2 minus a2 x1 plus b1u. Therefore, we've got the two state equations. The first one we have, which is just basically relations between the two state variables, and the second one that actually relates to the system that we're looking at here, x1 and x2. Now, all we have to do now is to write that in matrix form. Right? And matrix form means a vector x dot equals matrix A times vector x plus matrix B times u, right? And the corresponding output equation as well. So we can easily do that. Just looking at this, we see x1 and x2 are going to be our states. So x1 and x2. x1 and x2 differentiated is going to be our x dot, right? So this and this correspond to, if you like, this term here. And then we just have to look at the scaling factor. So x1 dot, that's this term here, equals x2, right? So we look in this matrix, so it's It's no corresponding input from x1, but it's got a multiplication of an x2 there. So 0x1 plus 1x2 gives us x1 dot. That's what we're saying here. And there's no contribution from the input, so there's 0 lots of u. The x2 then is going to be minus a2 times x1. That's that. Minus a1 times x2. That's that. Plus b1 times u. So that's that equation. And the output equation, in this case, we just want y to be x1. So we have a very simple equation there. So our C matrix is 1, 0 in order to select x1. Let's now quickly do an example of a DC motor. We've already looked at that, so that should be a bit easier to understand. So we've already said the torque of the motor is given by the current times the torque constant. And this is balanced by the resistance of the system to move. So it's resisted by coefficient of viscosity multiplied by, if you like, the angular speed, angular velocity of the motor. So b d theta dt. And it's also resisted by the moment of inertia, so j d squared theta dt squared. So this is j times angular acceleration. And this torque generated by, if you like, current passing through the coil in the magnetic field has got to balance the torque of resistance from the viscosity and also from the moment of inertia. So we get those two equations, sorry, those two terms on the equations. We did this before, but basically the other equation we've got to worry about is the voltage equation. So we're looking at it as an equivalent circuit. We say the input voltage applied is in terms of the current, it's the drop across the resistor, IR, plus the drop across the inductor, which is L di dt, plus the drop across the dynamo or the generator effect, which is going to be this speed of rotation multiplied by the generator constant. So that voltage plus that equals the applied voltage. And we end up with our second differential equation. And we're going to write that like we did before, actually, with on the left-hand side, the highest differential term in current. So let's first of all write down a second differential of the angle in terms of the differential of the first differential, right? So that's the first term. So we can do that. We're just saying that this is going to be effectively a state, and we differentiate. So this is going to be like x1, and this is x1 dot equals all of this stuff, which is what we have already over here. And we know also that di dt is the differential of the current, right? And we've already got what that is, right? So that we've already got that equation from before. So we've got the two equations now. We can now rewrite this equation in terms of d dt of I of t. So what we're saying now is we're choosing two states. We're not actually explicitly putting them in. We're choosing a state d theta dt as being x1, and we're still choosing a state I of t as x2. And this is just saying the differential of this state gives us this expression, the differential of this state gives us this expression. So those are our two effectively states. We haven't explicitly called d theta dt x1, and we haven't explicitly called I of t x2, but we could have done. We can now write these in matrix form, all the same though. So the state, this is the state vector here, d theta dt I of t. This is the differential of the state vector. So this bit here on the left corresponds to this. This corresponds to the state vector, and as we can see, it's now minus b over j times d theta dt plus kt over j times I of t, that times that, plus no contribution for the input, and I of t, that's differential, this equals minus ke over L times d theta dt, so that's that times that, plus this term minus RL, R divided by L times I of t plus 1 over L V of t equals this term here, right? So basically, and if we want to look at the output velocity or the output angular speed, we need a C matrix which will pick just that from our state vector in order to get the output. So we end up with basically these equations. The A matrix is given by this term in front of the state vector here. The B is given by this term here, and the C is given by this term here. Okay, and there is no D in this case.